Our last presentation is going to be much more hands-on technology type of presentation. Very interesting work being done by DETCRC in Australia. Richard Hillis, who gave a similar talk at the innovation session yesterday, will have a chance for an encore.
Thanks, Charles. Thanks very much. Gee, the last talk after 4 long days. I reckon. Right. Can my bosses allow me a little?
No one's sleeping.
A little light-hearted anecdote to start things off,
Sure.
seeing as it's the end of it. I don't know why this came into my head, but I have to get out of my head before I do the talk. And it's a story about the gentleman who performed the world's first open heart, well, obviously open heart transplant. Does anyone know who performed the first heart transplant?
South Africa.
South African?
Yeah, Christian Barnard.
Christian Barnard.
Yeah, Christian Barnard.
Does anyone know when?
Oh, it was 60.
Late 60s?
Yeah, 67.
Yeah.
67. And I'm not sure whether this story's true or not, but after he did it, the Australian Medical Association said, that's amazing, held a man's heart in your hand and transferred it. The guy would lived for 18 days, but it was the first time it had been done. Would you come to Australia and give a lecture about this world's first heart transplant? And he said, yeah, I'll come and lecture all around the Australian hospitals about this amazing feat, if you can just provide me a chauffeur to drive around so I can see your country. So Christian Barnard flies over to Perth, where Cam's from, and he gives this talk in a few of the hospitals, and he meets his, and everyone's in awe, of course, and then he meets his chauffeur in the peak cap and the jacket. He drives across the Nullarbor to Adelaide, where I'm from, gives it again. We did 3 hospitals in Adelaide, Flinders Road, given it 6 times. Driving down to Melbourne, and he says to his chauffeur, what about we just swap places? You've heard the talk 6 times, there's a bunch of slides, it's pretty easy. I'll put on your jacket and cap, and you put on my stuff and give the lecture. And the chauffeur says, oh, Professor Barnard, I could not possibly do that, you've held a man's heart in your hand. And he gives it 5 times in Melbourne, he's getting quite bored of it by now. The chauffeur's now heard it 11 times, tries up to Sydney, another 5 times. The chauffeur's heard it 16 times. Christian Barnard thinks, I don't even want to do this 3 times in Brisbane. He says, go on, be a story to tell your kids. The chauffeur says, all right, listen to me, I'll give the lecture. Change clothes, the chauffeur gets up like this, gives the lecture about the world's first open heart transplant, the aorta ventricle. He is perfect, absolutely word perfect. And at the end of the lecture, the surgeon, Brisbane Surgeon General, gets up and asks him this incredibly technical question, to which the chauffeur replies, sir, in all my years of giving this lecture, that is the stupidest, the stupidest question I've ever asked. And to show you how stupid it is, I'm going to get my chauffeur to answer it.
Yeah, that's good.
So, any questions? Straight to Ken.
There you go.
All right, it's been a long 4 days. It's a sort of blur of alcohol and meetings and talks and whatnot. So forgive me, I just had to get that on. Get on with it, we all want to get home. Mike Villeneuve talked very nicely. He said there's no sort of right philosophical construct there coming from the bottom up in the science, and you might start from the tools. No right answer. The right answer is to do what you do well. Our philosophical construct was to start from the tools that technology drives things, as opposed to the terrific science we've been hearing about. No right answer, just a question of doing what you do well. So, slide advance. That's what we're about. We're about technologies, and the truck there, just to remind you, CRCs are big things. I've done little of this. Other people have done it. Hundreds of people have contributed, so there's a truckload of co-authors. A bit about the CRC in case you're interested. Want to introduce this concept of prospecting drilling to you that we think is interesting. Just quickly on where we're at with the technologies and some of the field testing. So, here's the take-home slide, as we would say, that blurred out on that one. But really, we are focused on 3 technologies. Something called coiled tubing drilling. And just in case you can't get that with my accent, that means the drill string is continuous on a coil and you're not making connections to make depth. Much quicker, much safer. And I'll talk a little bit about how much quicker, how much safer. But coiled tubing drilling will not return a core. So the coiled tubing drilling has to be complemented by a suite of sensing technologies. And our suite of sensing technologies is downhole petrophysics. I don't know if that works or not. So downhole petrophysics that will do in real time, and top-of-hole geochemistry and mineralogy. And we are in fact commercializing those real-time sensing tools for conventional drilling as a step on the suite of tools that we will deploy with coiled tubing drilling. So that's really, if you've had enough, you can go home now, you've heard it, I'll just fill in some details. We do have a bunch of sponsors, and I do have to acknowledge them, because I'm sure my colleagues who've spoken before feel the same, that it's pretty rewarding to have sponsors stick with you through a very tough time in the industry. Our major sponsors are, I hate to say minor, but smaller level sponsors. There are, for those of you interested, about 40 cooperative research centres in Australia. And they cover a gamut of activity. There are some in wine and Aboriginal health and chickens, like literally. And they have in common that they're half funded by the Commonwealth Government and half funded by industry. So we have around $30 million from Commonwealth Government, around $30 million from industry to develop these new technologies. So it's a major research initiative, and the aim being to tackle a grand challenge. That's the point of a CRC, to tackle a significant challenge, hopefully. I think I've probably said what I wanted to say about that slide. A little bit more about the context. Many CRCs have their headquarters in universities or the terrific government research organisation, CSIRO. We're actually embedded with industry, so my office is in that picture, and that's Port Longyear's head office, which happened their APAC head office is in Adelaide. And we are very industry focused. And there's a key involvement of the suppliers, because an interesting thing happened when the companies funded DET, CRC, BHP, and Valley, and Anglo and Barrett, and co on. There was quite a bit of money, but they said, we don't want any of the IP developed. We have all this money, we don't want to touch the IP, provided you don't set up spin-off companies. We'll pay you to develop technology, but we don't want you setting up a spin-off company, because that will take ages, 3 years before they learn our invoicing system, 4 years before they learn our WHS, and 7 years before we've got a product. What you must do is license as quickly as you can to the existing service sector. So that is what we do. We license the technologies, and we have just signed a major license with Port Longyear for one of our pieces of key technology. So that's an interesting model, and you can reflect on that model. The background, I'm not the only one to use some of Richard Shoddy's slides. This is about discovery in Australia. The blue bars are tier 1s. The green bars, which are very faint from where I'm standing, are tier 2s. 75 through 2010, and if we look at say the period 94 to the end of that graph, there's a number of tier 1s, number of tier 2s discovered. Look at the 15-year period before that, significantly better, and in fact 80% of Australia's mineral production, which means 80% or 50% of its exports, come from mines over 30 years old. And other people have said it, and said it more clearly than me. Part of this, of course, reflects the challenge of exploration through blind cover. And we are about tools and technologies that will enable that more easily, enable us more easily to follow the sort of science that Cam's describing. That's what we're trying to do. So we complement the science, in our view. And we're not discovering because we're not spending money. We're still spending money. The blue bars are discoveries. The greenish background is spend, and we've got that horrible last peak where there's plenty of green spend and not many blue discoveries. Now Richard Shoddy would be the first to say there's probably a few to come through there, but it's not going to fill it in. And it's not like the previous two broad peaks. Does this pointer work?
I don't think it works.
You don't think it works? Okay, well it's not like the two previous broad peaks, one there and one there.
Let's see. It's the other end.
And I find it fascinating. There's a huge debate in Australia, and I'd love to know if it's in Canada too, about productivity.
It's fucked.
And Ernst & Young put out these very fancy reports, and they talk about the cost of labour and the cost of capital.
Yeah, but
and
it's
all the
not
rest of it.
working properly.
And incredibly, grade does
Two-handed,
not get a measure.
Two-handed laser.
Absolutely, incredibly. And the key issue, and the ABS has even said this, the Australian Bureau of Statistics has even said this, the key issue in the shocking productivity record of the Australian mining industry over the last 10 years is declining grade. It's the key issue. Now, I've got a couple of slides that demonstrate that. I like to make this productivity argument because it does seem to gel a bit better than just new discovery in the current downturn. That's why I'm sort of focusing on the productivity argument. It's not just an Australian problem, that's like maybe the wrong way. The back yellow is Australian mining productivity, increased for a bit, and then has decreased consistently over the last 15 years. But on that graph is also the US and Canada and Chile, and really there's not much to choose between us in terms of declining productivity. However, in Australia, this is to me an interesting graph. The solid black is MFP's multi-factor productivity, so not just labour productivity, all input costs, cost of capital, cost of infrastructure. And from 74 to 2006, productivity is about the same. There's been a decrease, increase, decrease. That's appalling. You know, most industries have increased productivity 100% of that period. But the dashed line, and this is an ABS report, the dashed line is productivity after the effect of declining grade has been removed. And in fact, productivity has doubled. But roughly speaking, we're pulling half the metal out the same number of tons. That's roughly speaking what's happened. And that is the key challenge. Australia, if it wants to improve its mining productivity, has to find new tier 1 good quality deposits and not continue to mine down the grade. And so a little bit of context, and I thought I'd do it from a productivity side this time rather than a sort of uncover discovery side. And that's just saying, you know, you can't make a silk purse out of a sow's ear. You know, that's a pretty well-known expression. Prospecting drilling. Prospecting drilling. So this is a term we've coined. And what it simply is, well, I should use my slides to talk about it. Start with this one. Here's a terrific map that Scott Hillis used decades of accumulated data. There are 23,000 top of fresh rock samples here from the West Australian goldfields. The map just shows antimony. That antimony at top of fresh rock is superimposed on the aeromag. The aeromag shows you those sort of north-northwest, south-southeast trends. The antimony appears to be lighting up or vectoring towards some of the significant deposits. Obviously, a lot of money spent on that drilling, as I say, 23,000 holes. Just do a little mental exercise and resample at a different scale. Could you get that with a little bit of drilling, in other words, if you came new to the area? Well, certainly not drilling at 8K spacing. Probably not drilling at 4K spacing. Drilling at 2K spacing? We starting to see some of the trends on the mag? Probably just about starting to see them. That would be a useful vector. In the drilling, there's about 250 holes there. In our coiled tubing drilling model, that would be about $1 million worth of drilling, we reckon. About $1 million worth of drilling. Would you pay $1 million for that information before moving into a new province? I suspect you would. And that's just one element. So, you know, we can't go on. I think I can speak confidently for Australia. We can't go on. This is an IOCG type diagram. That's terrific. All the earlier Murray's discussing the IOCGs. And that belt that he was talking about, typically people drill gravity anomaly. You're dead right. They don't even look for the shoulder of the mag anomalies. Most commonly, it's just a gravity high that's drilled. And there are thousands of gravity highs out there. And when you drill them with one hole, you generally don't get anything. Not only do you not make a discovery, you don't learn anything about the system. And the holes are expensive. I understand why that's done. It's too expensive to drill multiple holes. If we can enable cheaper drilling, we can use what we know about these footprints and vectors that so many groups are uncovering and progressively vector on the deposits. So there's current practice in the IOCG system. You can see many of these targets just at one hole on them. Lots of false positives, lots of problems. We're going to have to do something different, otherwise we'll just keep drilling false positives. And we know they have a footprint. We know these systems. This is our map of around a prospect called Emmie Bluff, which is in the Olympic Dam vicinity. The key thing is, I mean, the mineralogical comes from lots of holes, lots of high logging, lots of geophysical inversion, work by Simon van der Wielen. But the key thing is the scale of that diagram is 10 kilometers by 10 kilometers. There are many different versions, but that is something that if you drill multiple holes, you can start to use to vector towards. And we envisage drilling multiple holes vectoring on geochemistry and also using the geophysics. So starting with the regional scale inversions on the left, and as you get formation tops, as you get petrophysics, then improving those inversions while the rig is on the field and in the field and using the geochemistry and the geophysics to progressively vector towards the deposit. So hopefully that seems reasonable. Does the technology exist to enable that, or can we develop it? Let me give you a few minutes on that. 3 key pillars to what we're doing. CT, called tubing drilling, no core, complemented by downhole petrophysics, top-of-hole chemistry. Our stepping stone, though, is that we are right now commercializing the downhole petrophysics for conventional diamond and the real-time, both real-time, the top-of-hole geochemistry and mineralogy for conventional drilling, because that's a step to deploying the technology with coiled tubing drilling. Coiled tubing, first though, it's pretty amazing, and those stats are true. 2 to 3 hours time to move in and rig up to 100 meters an hour, 1,000 meter hole in, records kind of 24 hours for a 1,000 meter hole. $50,000. It's mostly used in Canada. Coal seam gas industry in Alberta is where the most coiled tubing drilling is being done. Also importantly for our sponsors, safety benefits. More than half the WHS incidents in mineral exploration are manual handling of drill rods. There is, of course, no manual handling of drill rods in this system. It is so much quicker because you aren't stopping to make connections. You're just continuously running out. I think I've got a little video, so I'll move on towards it. It's not completely easy, otherwise someone else would have done it. The petroleum systems are much bigger, they have blowout preventers, they are not drilling hard rock. They can afford to replace that steel coil every about 30 holes. So we need to be able to drill hard rock with a low weight on the bit. So a lot of our research is focused, and if you want to know more about that, feel free to ask me. We need a new tubing material that will last much longer and fit the sort of cost model we have. And of course, we have to ensure hole stability and sample recovery. And we've done a lot of work around those. But I guess it's sort of easiest to see. Here's a little coiled tubing rig. We bought this. Could you maybe just click the video? I suspect if I go on, it might just go past. Could the AV colleagues possibly just click on that and start it up? I'm not sure if it'll start for me. You're going to have to move your mouse and find the...
There it goes.
Thank you. So this is actually, this rig is designed for descaling geothermal wells. It's a very lightweight rig. That's the speed it's drilling at. So just in our very first test, there it is drilling it. That's about 50 centimeters a minute, 30 meters an hour. That is our first trial. We're using here downhole percussion. We're also experimenting with, so obviously the whole drill string isn't rotating. Sorry, I should have said that. It's all downhole motors. So either a PDM or a turbine. And that PDM or turbine is either driving very high-speed rotary drilling, talking about 8,000 RPM, because it's low weight on bit and a small depth of cut each rotation, so you need lots of rotation, or percussion, which will always drill quicker in hard rock. You can probably see it's finished now, but it was going in about 50 centimeters a minute in that example. So we have both. We actually run a drilling facility in the Adelaide Hills, where we do tests like that, but of course we're doing lots of research at various facilities around Australia into the nature of the coiled tubing material, into the downhole tooling that will drill hard rock with low weight and bit, and into hole stability and cuttings recovery. And in fact, that's how it looks now. That's the board along your shed at Adelaide Airport. We've taken the steel coil off it, and we've got something called a flexible hose on it. You can see it's a flexible hose by that sag between across the rig. And if we can drill, it's probably about the most exciting 6 months in the CRC coming up. If we can drill with that, we're going to deliver very, very cheap drilling. Our target, for your interest, is $50 a metre. Might not sound really cheap in Canadian costs at this time in the cycle, but that is cheap in Australian costs. $50 a metre, $100 a metre program rate. That would, for example, do that program I showed earlier at $1 million. A rig weighing less than 10 tons. So very easily in and out, only trying to get to 500 meters. Now, coiled tubing can of course drill 4 kilometer lateral wells along the oil-water contact if you've got a steerable sub on it. We're not doing that at the minute. We're just doing baby steps to have a greenfields rig that will go down, do all the sampling, and do it very, very cheaply. That's what we're about, and you get a sense of the progress. We're already drilling holes and just really testing things now to get the cost model down. Look, here's some cost numbers, and the absolutes don't matter. Drilling costs are higher, and these aren't bottom of the market figures, but the relativities matter. So a program that I might say, a diamond program that might have cost you 3.25 mil and taken 100 days, our target is $500,000 in 20 days. And so we believe that's a sort of cost change that would permit prospecting drilling. And there's another scale. The reason coiled tubing drilling is so cheap in Alberta is they're tuned. They keep drilling essentially the same hole. So if you're drilling the same geology, it's the same bit, it's the same crew, you know the weight on bit, you don't mob and demob, you stay out in the field, that also drives all your costs down. So if we're not going to return a core, we need to get information from the hole. There's no point drilling a hole. Two things, downhole geophysics, and I said that our initial products are with conventional drilling, and so our initial, and then it's easier, that's a big step towards putting this sort of sensing on the coiled tubing rig. And the auto sonde has just been commercialized by Boat Longyear. Driller gets a conventional diamond, driller gets to the bottom of the hole, pulls the rods off the bottom of the hole, doesn't need to phone up a wireline crew to come out, and separate crew, separate mobilization. He just has the probe, which looks like this, pumps it down the hole, it goes through the drill bit, locks in at the bottom of the drill bit, and logs as the rods are pulled. You're not taking any extra time, you're not going to lose the hole before you log, and the driller just downloads it Bluetooth. This works. Our only sensor on this at the minute is natural gamma, so if you're doing uranium or potash, you're looking for some potassic alteration handy, we are gradually putting more sensors on it. The next one will be MagSUS, the one after that, resistivity. In fact, there are two platforms. This is deployed after drilling, through the rods, logs as the rods are pulled, no extra drilling time, no wireline crew. We're also putting sensors on something called the shuttle, which sits behind the core barrel. And that is closer to real time. Tougher environment because you're rotating, because fluids are coming through, it's vibrational, but a longer residence time at the rock face. So for example, we're going to put spectral gamma in that platform because the residence time is critical. In that case, we also have to sense through a rod, which you don't have to do in the sonde. So those are our sensing tools, and petrophysics is of course routine in the oil industry, and there were some terrific comments about that earlier. It's not routine in the minerals industry, in part because holes collapse, in part because the cost model doesn't work. This is just simply about making it no extra time and cheap, and we believe it will become routine and actually be the key to some of these interpretation and linking geophysics and geology issues. We're at, I think I probably said all of that. If I would it go, or will I? Yeah, no, as I thought, I'd just go on to the next slide. So, again, could our AV technician possibly wiggle the mouse and click the video? I don't think I can do it from here. So that's just it being deployed. I might not even worry about showing you all of it, given it's so late in the afternoon, but that's the sonde. That is a driller, not a wireline crew. He's about to put it in the hole, pump it down the hole. It will traverse down the hole. It will go out through the rods, and he will record a log as the rods are pulled. And in fact, what Boat Longyear have done is combine it with an existing survey tool. So if you're going to do a survey, it is 0 extra time, because it's just combined with the survey tool. I'll just go on. That's a comparison. I hope you can see it. The dark solid line is, so a couple of our test holes, the dark solid line is wireline, conventional wireline. The grey is from the sonde. So where there's a gap between the grey and the solid, there's a slight difference. So this area here. But I think you can see in general it's pretty, the fidelity is pretty good. Geochemistry, we basically said if you're not going to get a sample, but it's cheap, and of course there's a cost-benefit trade-off here, we want petrophysics, we want an image, which I haven't had time to talk about, either acoustic or electrical, so we can get structural information. We want geochemistry and we want mineralogy. And we think, and you're welcome to pick me up on it later, we think most geologists will trade objective, continuous, entire hole measurement of those 4 parameters at a very cheap price for core. So that's our proposition. The Labbit rig was really interesting. We actually started trying to do downhole geochemistry, something called prompt gamma neutron, but it wasn't successful, or it wasn't successful enough. Another long story. And one reason we stopped, and I'm going to skip that one, is we were terrifically encouraged by this early piece of work we did. So our first test hole, it's a diamond hole, confusingly depth is horizontal. The blue bars are simply geologists' log sulfide. For Cam's benefit, David Giles' log sulfide percentage. But we also looked at the drill powder, the annulus. It turns out that actually there's almost exactly the same annulus volume as there is core volume in HQ. About 9.8 kilos of annulus volume, about 9.5 kilos of core volume per meter, depending on the density. But you don't bother looking at that, do you? Because you've got core. We thought, well, we'll have a look, because if all we've got is powder, how reliable is it? And so the blue bar is log sulfides from the core, and note that little stringer at about 100 meters. The yellow is simply, so all we've done, this was just the driller going up as in conventional petroleum mud logging, sticking in a trowel, taking a sample. No solids removal unit, some of it might be going around twice, 3 times, who knows. And then portable XRF performed on that rock flower from the kerf, or drill cuttings, whatever you prefer to call it. And I guess we were pretty surprised at the yellow sulfur, the red's iron. We were pretty surprised at the depth fidelity of that. And you see it there in the little stringer, and you see how it pretty quickly drops away. And we said, well, maybe this is pretty reliable, particularly, again, if you combine it with the petrophysics, which lets you actually map the boundary. We've done a lot of work since then. I'll actually put light on slides on that. Done a lot of work since then. The elaborate rig now is combined with something called a solids removal unit, the index solids removal unit, which is used environmentally to stop you having to dig sumps. But it is also a sample recovery unit. And when you are conscientiously recovering sample each cycle, the depth fidelity gets even better. And we are drilling holes. We've got a deployment with Anglo-American in New South Wales, where we have 10 centimeter depth fidelity in a diamond hole at 600 meters. We can pick up a 10 centimeter unit from the drill car, the drill cuttings. Field tests, I guess, there has been a lot of enthusiasm, and I think something Australia does well is collaborate between its agencies. So we have collaborated with the surveys, wherein the geological surveys wish to drill greenfields territories and discover new provinces undercover, and we've project managed that drilling, whereas we want to try and pull through our technologies. I think that's been terrific collaboration. So the Geoscience Australia, Geological Survey of Victoria, DET, CRC all collaborated in a bunch of drilling in Western Victoria. The surveys were interested in mapping a Cambrian Andean type margin undercover. There are sniffs of porphyry there. It's an interesting province. We were interested in pulling through the elaborate rig technology. So that's probably allowed us to take, just put more kilometers on the clock of the technologies than we expected to. That's our drill test site. This is disused mine. I sort of sometimes feel defensive that we run such an expensive research organization, but we do have a drill site operating for 7 years, testing technologies, doing some training as well. And of course, at risk of belaboring the obvious, not only do we test new drill bits and whatnot, we drill diamond core there and use that to calibrate our various downhole sensing tools. There's about 10 holes there now, and there's mineralization. That was the stable drilling that we did recently. So the surveys looking to uncover new provinces, but saying, even if we find a new province, there are too many false positives to just keep exploring these new provinces the way we've explored them before. We need some new technologies to explore these new provinces if we uncover them. And that's the sort of output that we were producing. This is just a product. This is the sort of output we were producing in that stable drilling. So the geologist was seeing this before he saw the core. Multi-elements, you've got chemistry, quantitative mineralogy. If anyone knows the area, it's the Grampians. So the top is Grampians metasediments overlying Cambrian volcanics. And in fact, you can even start to map the potassium starts to map flow boundaries in the volcanics. You can really see some quite detailed stuff in this, and as I say, the impact of the geologist seeing this before core was terrific. So they are sensing technologies that are now going out to conventional drilling, but I do repeat that our real driver for developing one is because they are critical enablers
Because you
of
can
this
calculate
cheaper
physical
coiled tubing
properties from
drilling.
the minerals.
And deployment of the existing technology is a step along the road. We're going to do a bunch. This is my favourite slide about South Australia. I live and we're based in Adelaide, so I sort of always feel obliged to promote South Australia a little bit. And the top bar there is the size in million tonnes of South Australia's biggest copper deposit. The second bar is its second biggest. And Cam talked about the fractal distribution of mineral deposits. I've looked at the fractal distribution of oil fields. They are not distributed like that. If ever there was a statement that province had uncovered IOCGs in it, or covered IOCGs around found, that graph tells you that. And the reason they aren't found is that when you've got 40,000 gravity anomalies, drilling one hole on them and learning nothing from that hole is not really changing what we do. So we're doing a bunch of drilling with the Geological Survey of South Australia this year. We're putting more kilometres on the clockwork technology. They're wanting to map the mineral systems better because they want those sort of vectors that will be the map, if you like, that where the technology can use. Look, you might be interested. We have a bunch of education and training, so it's not a small venture. I think that's out of date. I think there are 50 PhD projects sit within the CRC. So it is quite a significant venture. And look, my last slide, I'm sure you're desperate for me to shut up. We are about much cheaper drilling. Our much cheaper drilling is called tubing drilling. We're not going to get a core, but we're going to do a bunch of sensing that, I'd even argue with you after a couple of years now, say is better than core, because you will have mineralogy, you will have petrophysics, you will have geochemistry for the entire hole. And I think we will also discover serendipitous things because we're looking carefully at intervals we probably wouldn't even have logged before. And that will enable prospective drilling. Thanks very much, guys.
Hey. Any questions for Richard? A stretch. A question.
How does that flexible tube move the drill bit?
Yeah, so
Down the hole.
There's an injector.
Yeah.
So you mean push it down or rotate it?
Both.
Okay, so push it down, there's a gooseneck and an injector, so the injector actually pushes it into the ground, but it is low weight on bit, you're talking about 500 kilos rather than 10 tons. How does it move? It's all downhole motors, so there's no top of hole rotation.
Yeah.
Okay, so you either have a pressure displacement
That's
motor
well-known technology.
or a turbine.
Yeah, it's well-known technology.
And one of the ancillary benefits, not only is the bit always on the bottom, but you're not wasting tons and tons of diesel rotating a giant bloody 10-ton drill string to move a little drill bit at the bottom, which is what we do and have done for 100 years. You just have a little motor at the bottom. The motors are driven by the weight of the fluid, whether they're turbines or PDMs. So yeah, that's how you do it. The string is not rotating. I think we can all work out it wouldn't work with it. It would get in what a Scottish person would call a fankle if you tried to rotate a coiled tubing string.
Angle holes.
Yeah, so no problem with steel coil. They drill 4 kilometre horizontals with coiled tubing. If we go to the flexible hose and a longish, rigid bottom hole assembly, then my drilling program manager says he's probably not keen to go much below 60 degrees. In other words, from vertical to 60. Petroleum minerals say it differently. And once you haven't got a bit of gravity helping you with that flexible hose, it's probably not going to go. So the steel coil, you could do up holes underground, but the flexible coil, which might be the one that fits the cost model, between 60 and 90.
Mike?
How do you control the direction?
Yeah, so in our assembly, we would just be trying to get it drill straight. This is a greenfields rig, we've got 3 challenges. We'll have a rigid bottom hole assembly. It will drill reasonably straight. How you actually drill, if we're successful, and people say, oh, this is so fabulous, we now want to do delineation drilling with this and be able to, you have something called a steerable sub, which is a piece of pipe just behind the bit with an elbow joint. And you communicate with that and you say 1 degree. That's how, so in the petroleum business, they would have that with a real-time resistivity. And the real-time resistivity tells you whether you're in the gas leg or the water leg. As soon as you move up into the gas leg, they send it down. As soon as you move into the water leg, they send it up. So a bent sub.
Okay, any other questions? Good. Good. Thanks, Richard.
Thanks,
Great.
guys.